So as we saw, as we move from a abelian group to a non-abelian group, so we need to expand this definition of character, not just look at this character as representations from G to the unit circle, but also we want to replace this unit circle by some operators on B of H. And a unitary representation is essentially just a representation that makes it into the unitary group. Okay, so here's the definition. So a unitary representation of a locally compact Hausdorff group G, so here G may not be abelian, so that's going to be a star homomorphism, let's say pi, from this G to the B of H. Well, this H may depend on pi, so usually we just write H underscore pi. And then we have the following conditions. So first of all, each of these pi x is going to be a unitary. So that's for all x inside G. And second, I have is a homomorphism. So the pi xy is equal to pi x pi y. And I have if I consider the pi x inverse, well, it's going to be the homomorphism. So the involution basically on B of H is taking the adjoint. Okay, so to the adjoint. All right, so that's basically explain the star homomorphism. And finally, we need some kind of continuity. And the continuity is actually we just require it to be SOT continuous. Okay, so pi is in fact, so the G has a topology, let's say tau, and then the B of H is equivalent with the SOT topology, and that's SOT continuous. Okay, so in other words, now what you're saying is that if you evaluate at any H inside your Hilbert space H pi, then this map from X to this pi X of H. Okay, so this is a map. This is a map from on the left you have from G, on the right hand side you have in H. So that's going to be a continuous map. Okay, so that's the same. And as we see, because your range of this pi is the unitaries, so the weak operator and strong operator also coincide. So this pi equivalently can say this is tau with weak operator continuous. Okay, they're essentially the same thing. All right, so this pi in your mind. This is going to replace the character group for in an abelian case. Okay, and we'll see why that's the case. All right, so now we need to do a little bit more definition. So let's consider the following. Let's talk about how we can break these kind of representations into sub-representations. Okay, so a lot of the time these representations are built from a direct sum of a bunch of representations. So let me just write it. So let's do remark. So in fact, if you have say pi 1 and let's just say pi I, from G to the B of Hi, and you do the following. So if you consider pi 1 direct sum pi 2, okay, you call it big pi. So you define it as from G to the bounded linear operator from H1 direct sum and H2. So what it does is essentially just maps X to the following operator. So things in H1 plus H2, you can think about it as a 2x2 matrix. Okay, where your operator kind of going from H1 direct sum H2, that's your takes a vector from there and you map it to a vector in here. So you can always write in this operator matrix. So what you do is you put the pi 1 of x here and then you do the pi 2x here and then you say, well, that's 0. So sometimes we also write it as just the direct sum of these two operators. So they're essentially the same. So as you can see, this is going to be again a unitary representation. Okay, as long as your pi 1 and pi 2 are unitary. So if pi 1 and pi 2 are unitary representations, then your pi, which is their direct sum, is also a unitary representation. All right, so in other words, a lot of these representations are coming from these kind of direct sums, and you want to break it into the smaller ones that's not a direct sum. Okay, so that's kind of an idea of the irreducible ones. Okay, so let me just introduce what they are. So let's talk about, first of all, what's a invariant subspace. So let's say given let's say pi that's a unitary representation. Let's say this pi is from G to the bounded linear operator on H pi. A subspace, let's say H contained in H pi, and whenever we are in a Hilbert space, whenever we say a subspace, we automatically will mean a closed subspace. Okay, that's just the convention. So a closed subspace is called invariant under this pi, or for pi. If the following thing happens, if whenever I have say pi x, or let's just say pi g, that's basically a bunch of operators, a bunch of unitaries, and if I apply it to H, then I always get something inside H. Okay, so in other words, if you take any x inside G and you take any H inside H, you always have your pi x times H that's still inside H. Okay, then this is H is going to be invariant. Okay, so it's kind of this pi, the image of this pi will act on H and maps H back to H. And so whenever you have something that's invariant, in operator theory, that's usually tells you certain part of it is going to be certain part of the operator matrix decomposition is actually zero. So let me just briefly remind you something in operator theory. So let's say in operator theory, and so if you have some operator, let's say A inside B of H, and let's say H, say B of H, and you have H0 contained in H is invariant for this A, if basically your A times H0 is contained in H0. So how do you understand this is the following. So if you decompose your H, because we're in Hilbert space, so everything can be decomposed as is H0 and is H0 perp. Okay, so your operator, this A, you can think about it again as a 2x2 matrix where it takes H0 to H0 perp, map it to H0 plus the H0 perp. And if you think about it, you feed in a vector, let's say H, inside this H0. So this matrix A will map it to AH, which has some part in the H0 and some part in the H0 perp. And the fact that H0 is invariant is essentially just saying this part is going to be zero. Okay, so this is telling the H0 is invariant. All right, and so of course you can have something here and something here, and that doesn't really matter. So what matters is that this corner is equal to zero. And but if you think about what happens when you have representation now, because your representation, so here, because if your H is contained in H pi is invariant, then not only you have this, so each of these pi x, if you look at its decomposition as H direct sum H perp, H perp. So because the H is invariant, so automatically you have this corner is going to be equal to zero. But if you think about what happens to the H perp, okay, so because your pi x inverse times ch is also contained in H, so that just implies the pi x star of H is also contained in H. Another way of saying that is this is actually just equivalent to the pi x if you apply to the H perp, that's contained in the H perp. Okay, you think about when you take the adjoint, you adjoint this 2x2 operator matrix, and the H is still invariant. And that's essentially just saying this corner is also equal to zero. Okay, so let me maybe change the color. So this corner is also equal to zero, which follows from the H perp is also invariant. Okay, so in other words, whenever you have something that's invariant, its perpendicular space is also invariant. Okay, so is invariant for this pi. Okay. All right, so in other words, as you can now see, this H has these two corners are both equal to zero, so it can have something in here and something in here. So if I give it a name, let's call this pi 1 of x, and you call this pi 2 of x, okay, because this is these two corners are zero for all the x. then automatically what you have is that this, if you let just say pi1 of x to be equals to your pi of x restrict to h, which you treat it as a operator from h to h, and you let pi2 of x to be the pi x restrict to the perpendicular space, you treat it as a h perp, because it's also invariant, so that's also in h perp. And from there, you can see that this pi1 and pi2, they're both representation, they're both homomorphisms. They have to satisfy the star homomorphism. And because you have on these two off diagonal, you have 0, so these pi1 and pi2, they have to be unitary on their corresponding space. So we have these pi is essentially just the pi1 direct sum pi2, okay? So in other words, whenever you have a invariant subspace, okay, you automatically can decompose it into two smaller parts, okay? It's automatically a direct sum of two sub-representations, all right? So now let's give it a definition. If you can't really decompose it non-trivially, then we call it irreducible, okay? So we say pi is irreducible if basically there is no non-trivial. So non-trivial means either the 0 or entire space. Okay, there's non-trivial invariant subspace. Okay. Okay, in other words, your pi cannot be decomposed as a direct sum of two sub-representations. Okay, so this is the definition of irreducible. And of course, if it's not irreducible, we call it reducible. Okay, so whenever you're reducible, it's actually a direct sum of their sub-representations. So there's one special case of these invariant subspace. Let me probably do this observation. So if you observe the following, so let's take any, say, vector u inside this h pi. And what you do is you consider the kind of the orbit of this u under your representation. So if you consider all the pi of g, okay, evaluate on your u, so here g is inside g. And then you do the linear span, and you want to make a closed subspace. You do the closed linear span, and you call this space M of u, okay? So if you think about what happens to this M of u, well, if you take any, say, h, any h is equal to summation of some pi of gi ui inside the M of u, let's do some finite sum first, I going from 1 to n. And then you do any pi of x, okay, and you apply it to h. Then automatically, because your pi is a unitary, so it's a representation, so this pi of x will go inside. So this is essentially the summation of pi of left translation of these gi, hi. But the thing is, this is still inside M of u, okay? So this is going to be invariant under all of these pi x. So in other words, your M of u is always invariant, okay? Invariant for pi, okay? So in other words, you can always kind of find these invariant subspace. And of course, if your pi is irreducible, then this M of u being, well, of course, if you take u being non-zero, then you get something that's non-zero. So if your pi is irreducible, then this h pi will be equal to this M of pi. And these kind of representation will give it a special name, okay? So these, because their space can be written as kind of the span of the image of certain one single vector, so we say these are called the cyclic representation. So here's the definition. So if I have a unitary representation pi from g to b of h pi, we call it cyclic. If I can find a vector u, which is usually non-zero, okay, so that this h pi is equal to the M of u, okay? So as long as I can have one thing that's kind of span the entire space, then I call it cyclic.